Hello physics students, this is Dr. Brenzi here, and this is the video notes on lesson 2.2.2. Today's lesson is going to be talking about inclines. So we have a box or mass on an incline, and it is going to slide down this incline. We know that from personal experience, and we need to find out interesting things about it, like its acceleration, and we can find out some other things about it. Like the normal force that this block experiences due to the surface of the ramp itself. So, first of all, I want to show you how not to do it. Now, we are very used to having... actually, let me go ahead and just draw a free body diagram here so we know that this is the normal force, and we know that this is the force due to gravity, and we know that this is the friction force. And we are very used to the accelerations in that direction, down the incline. We can expect that. And we're very used to setting up coordinate systems where x is to the left and right, and y is up and down. And we've been taught that since we've done Algebra 1 or maybe even pre-algebra in 8th grade. But if we're going to use this coordinate system, we have to break down a lot of these forces into their x and y components. For example, we would have to break down the normal force into its x and its y component. And then we would have to break down the friction force into its x and its y component. So now I've already had to break down two forces into their x and their y components. Now thankfully the force of gravity only has a y component, so I wouldn't have to break it down. But here's what's even worse about this, is that I would have to also break down the acceleration into its x and y components. Well, actually that's not quite true, because what would result is that I would get an acceleration in the x direction, an acceleration in the y direction, and then I would have to figure out the magnitude by using the Pythagorean theorem. Alright, so I'm breaking down lots of things into components, and that could be not only tricky, well, maybe not so tricky, but it's laborious, and it can produce a lot of errors. So let's be smart about how we do this here. So let's not make a coordinate system where y is going straight up and down and x is going left and right. Let's choose a coordinate system that makes our calculations easier. I'm going to rotate this coordinate system so that the x direction goes along the incline. It's parallel to the surface of the incline, and y is perpendicular or normal to the incline. Now, if this really bothers you, what you can do is turn your piece of paper. Now, I can't do that with the screen, obviously, but maybe you can turn your piece of paper, and that might be more helpful for you. So what would these forces look like with this coordinate system? Well, the gravitational force, of course, still goes down, and when I mean down, I don't mean in the negative y direction. I mean down toward where the center of the earth would be. So it doesn't get rotated. The friction force, the normal force, and our acceleration. Now what you'll notice is that when I tilted this coordinate system, my acceleration only has an x component, my normal force only has a y component, and my friction force only has an x component in the negative x direction. So the only force that I have to break down into its x and y components in this rotated coordinate system is the force due to gravity. Whoops. I don't know how I did that, but let's see if we can go back. Okay, that's odd. I thought I had made... I thought I had made more notes about that. Okay. Well, Actually, what I'm going to do, I thought I wrote more notes about this, but I'm going to go ahead and break down this gravitational force for us. Or do I do that on the next slide? Let's see if I do that on the next slide here. Sorry about that. So let's say, for example, that I want to find the acceleration of this block down the ramp. Like, how fast is it accelerating down this ramp? So let's say that this mass is 10 kilograms and this block, or this incline, excuse me, is at an angle of 30 degrees. So let's draw our coordinate system. Let's draw our normal force, which is always perpendicular to the surface. Let's draw our friction force, and that, as I said in the previous slide, has a negative x component and only negative x. So I'm going to draw everything that has only x components in red, and I'm going to draw things that only have y components in blue. That'll help us differentiate the two when I have to go and actually write Newton's second law for the x and y directions. So I'm going to draw F sub g in purple because it has both x components and y components in our rotated coordinate system. And the acceleration is only in the x direction in my rotated coordinate system, so I'm going to draw that in red. So let's go ahead and break down the force due to gravity, which is always pointing straight down, no matter, well, straight down on my piece of paper, I guess, but not in negative y on my coordinate system. So let's break it down into an x component and its y component in my rotated coordinate system. Now be very careful about this because we're used to drawing our right angle either here or here. But in this rotated coordinate system, my right angle is actually right over here. So be careful. Be careful about that in your rotated coordinate system. And as a matter of fact, I would suggest rotating your paper when you're trying to break this force due to gravity up into its x and y components. When we go to break those up into x and y components, we know that this is an angle of 30 degrees because this angle is 30 degrees. So this x component is going to be f of g times sine of 30 degrees because sine is opposite over hypotenuse. The y component is going to be negative fg cosine of 30 degrees because cosine is adjacent over hypotenuse. And I put this minus sign in front because it is going in the negative y direction. Okay, so let's go ahead and write force equals mass times acceleration. It's Newton's second law for the x direction. And when I do that, I have, for F net, I have negative F sub F, because it's in the negative x direction, plus F sub g sine of 30 degrees. And that is going to equal 10, which is the mass, times the acceleration. Now I'm going to assume that the force due to friction is 5 newtons. I would have to give that to you in a problem, so I forgot to do that, but I'll do that now, which is why this is negative 5 down here. Equals the force due to gravity, which is 10 times. Now, I need to be a little bit careful here because a lot of us are used to writing negative 9.8 in here, but I've already considered what sign it's going to have when I broke it down into components. So in this case, I'm actually going to just write down 9.8. Okay? And again, the reason I did that is because I already have the correct signs in front of F sub g. And then now I write in sine of 30 degrees equals 10 times A. let's continue our work over here. So I have negative 5 plus 49. You might be wondering, why did I write 49? Well, if I take 10 times 9.8, I get 98. And then sine of 30 degrees is 1/2. So 98 times 1/2 gives me 49. And all of that equals 10 times a. Well, I can simplify that left-hand side so that 44 equals 10a. And that means my acceleration is 4.4 meters per second squared. Okay. So, it's slower than the acceleration due to gravity, right? Yeah. Okay, now for our second example, let's find the normal force. I put time in there, but I'm going to say the normal force. So let's say we want to find the normal force that this surface exerts on this block right here. So let's draw our modified coordinate system. Let's draw our normal force, which is always perpendicular to the surface. And the only other force along the y direction in our rotated coordinate system is the y component of the gravitational force. All of the other forces that we drew are forces in the x direction. So, when I go to set up Newton's second law in the y direction, all I have is F sub n minus the y component of gravity, which is negative Fg cosine of 30 degrees. Now that is equal to mass times acceleration in the y direction. Well, if my acceleration is all in the x direction, what does my acceleration in the y direction have to be? It has to be 0. There is no acceleration in the y direction in this rotated coordinate system. So I have an equation that I can solve for F sub n. Because I know the mass, I can figure out what Fg is. And as a matter of fact, I'm going to plug that in over here. So the normal force minus 10 times 9.8 times cosine 30 equals 0. Sorry about that little, I ran out of room there. Sorry about that little upswing there. And when I add this term to both sides, I get the normal force equals 98, which is 10 times 9.8, times cosine of 30 degrees. Well, that turns out to be the square root of 3 over 2. And when I multiply all three of these things together, I get that the normal force is equal to 85 newtons. Now that normal force is less than the force due to gravity on this block. F sub g, you know, is 10 times 9.8, which is 98. So when you have a block on an incline, the normal force is going to be less than the force due to gravity. So be aware of that when you're being asked problems of blocks on an incline, is that the normal force doesn't always have to equal the force due to gravity. Okay, well, that's all I want to cover for now because this video is already running up to 15 minutes. But there are other interesting problems that we can do, and we're certainly going to practice those in class. And I look forward to seeing you in class soon. All right, take care. Bye.